As it turns out, we will be finishing the lectures just as spring break arrives, so we've got 2 more weeks. And then after spring break, you guys start presenting your term project. I haven't had too many people coming to me with a term project. I'm sure a lot have been discussing with Professor Eager. It's probably now a good time, if you haven't made a lot of progress, to get started. I'm happy to talk. I'm here. It's easier if you send me an email and we can schedule a time.
Yeah, if you've got a second, I can just say a couple of words about what this topic of your choice. No more than about 10 overheads, because you've got 10 minutes to do it, okay? If you go past 12, I'm actually going to get up and yank you, okay? So, it's got to be brief. Topic of your choice so that you'll do a better job on something you're interested in. I am going to send around an email asking if you're going to be doing something that relates to intellectual property, the health stuff that Neil's done, or the structural material selection that Dr. Belmar's done, just so I can figure out which days to make the presentation so that people can be here for those things, okay? I've already sent around a schedule with some of these things. But if you have some questions, I mean, you need to kind of pick a topic. In years past, people did pole vaulting poles. What was yours last year?
I didn't do it. I was in the process.
Okay. Carolyn, you did pipe pigging, okay, inspections and pipes. Anybody else in here? Oh, nobody else in here has done it before. But anyway, so you're welcome to come talk to me before class, after class, or make another appointment to talk about it. But it doesn't have to be long, it just has to be good. Okay?
So you said 10 slide, and how long do they have?
They have 10 minutes to present, okay? And it doesn't have to relate even to these particular 3 modules, because not everybody's taking the same modules. Just a topic of your choice. Hopefully it will relate somehow to materials or intellectual property or health or something, okay? But it doesn't even have to do that. Okay.
All right, so given that we're finishing in 2 weeks, the only module that's going to be, of course, 14 units is the intellectual property one. Everything else, like my section, is going to go truncated this term. I'm going to do 8 lectures, so we got today and 2 more to cover the use of material, which is doable. So today we'll switch. If you remember what we spent the time so far, we spent about 4 lectures of material selection, trying to put it in relationship with what we're trying to do. We're trying to fulfill an objective. We have a bunch of constraints, and we've looked a little bit at the difference between the metals and the polymers. We talked a little bit about composites. Today we're switching gear a little bit. We say, okay, so we know what we want to build. Let's just assume we know exactly. And the next step is, how do we ask, the fabricator, or how do we put on a design document what we're looking for? The slides are already online, and I was late to the printer, and the printer, that's when the printer don't work well. So it may come later, or you could ask for a hard copy. I'm sure we'll have a hard copy later. But it's a lot of images today. I want to try to bring you to think, okay, I know what I want, but now I do have to communicate it. I want something that's going to have a certain chemistry, certain properties. Perhaps it's going to need to have some inspection done to it before I use it. These are all things that are not, you shouldn't take for granted. If you ask a shop to manufacture something for you, don't assume that they know exactly what you're going to be using for. So if you're the one essentially laying out the groundwork on material selection, perhaps even on the design geometry, then you do have your part of work to do here. So I had a lot of examples that I was thinking about putting forward. I picked one that was perhaps looks very, very simple. This is a big fontaine that was about 60 feet long, just right off Central Park. in New York. And it was meant to be, you know, very architectural. So if you look closely at some of the panels of that, more or less of a sculpture, it has a lot of surface features, that it has little holes. These were all designed, so there's an artist that was putting together this mold and decided, okay, we're gonna make these panels just exactly like I want. And it's a bronze alloy that's gonna age in a certain way. So this is all, you know, custom made, very expensive. In the end, it's a tunnel, like I said. So it has 2 panels on each side and then a panel on top. And over here, it's about 60 feet long. And then there's a lot of mechanical systems on the inside of it, so that's the 60 feet. A lot of mechanical system to supply water. Now at that point, it really, nothing was working, so it's just leaking here. But I've seen it work when it was completed. It was beautiful. You know, you get the water to fall from the top, and there's the little ports here. These are special lights, so at night it will show very nicely what's going on. There were a lot of people involved in making this project happen. Structural engineers, there's a metallurgist, there's also, of course, the artist that had some experience, and there's a foundry. The foundry made these panels that were about 10 feet long. So over here, what you see is a joint between 2 castings. So they were pretty big castings. And they had to weld the 2 alloy at the corners here to make this U shape, and they also had welding to connect the 2 different panels. Now, over here, it wasn't as big a deal because the panel did come with an edge, so it had a lot of area here, if you will, and they were putting bolts here too on this connection. Over here was just a welded joint. So the kind of the highlight of the project is the bronze was selected and specified just by its normal designation. So you have the Copper Development Association, CDA, that arrived with a 3-digit system to list copper-based alloys. And they have different categories, whether it's a casting, whether it's going to be a product. In any event, you pick one of those, and what it will tell you is what the chemistry is. So and you can go online, this is, you know, all listed, and you can ask, okay, if I take a certain alloy here, what are the mechanical properties, the physical characteristics, the casting characteristics? So what the CDA does really, it's applying a chemistry. But at the same time, if you go online, what you'll find is there's a typical product. And Matt Weld would do that, right? It will just say, okay, you have a certain alloy, well, it can have these properties. So in the typical here, if you have mechanical, anybody can go and provide some information to feed in here, but it's not necessarily going to be real. It's going to depend on how exactly the material was manufactured. Especially with casting, there's a lot of ways to control, for example, the oxidation, control the environment, the interaction with the mold that can make a casting either very ductile, that it will deform before it breaks, or very brittle. In this specific case, it's always easier after the fact, and you know, we won't get too much into failure analysis this time. We don't have a whole lot of time, but you know, after the fact, you can think of this as, okay, it's 60 feet long, it's metal, and it's sitting on a concrete foundation. It has to sustain, you know, winter and summer, so it will expand and contract by, I think I estimated is how much this would want to expand in contract. So there will be stressors in it. And the only way to resist stressors with such a complex structure that has welding, it has holes, is to have ductility, to have a metal that if locally, where you put the bolts, it somehow wants to apply a bigger load than the nominal load. There's a localization essentially of where the forces transfer. They'll just bend a little bit and continue on. So what the problem here was, is they were relying on this whole structure being a little bit like a piece of steel that, you know, if you beat the steel, yeah, you know, it may deform, and you may get a little dent, but it's still going to hold together. But here you have something that's really thick. The wall thickness on this was about 3/4 inch. And that was essentially a limitation because of how the characteristic they wanted to have. So this is very heavy. And it wasn't supported on rollers or something that would just allow it to expand in contract. We talked a little bit about this when we were discussing plumbing system. I said, you know, if for example here, I just hold the metal to the foundation and I allow each side to expand a contract for the season, that wouldn't be a problem. You know, I could just have a special roller system here and each end will move by 1.5 inches. But if you don't make those provisions, I think your only other option is to say, well, I want the chemistry, but I also want certain properties. I want the alloy to be able to deform before it starts cracking. It was, you know, very consequential mistake in the sense that each panel was just custom made when it's built, and now it's not really resisting any of the environment. They had cracks at the beginning, and then will continue having cracks over time. Do I see some cracks here? Maybe it's not showing, but the biggest crack was about this long, just after the first winter. It's just a question of what you're looking for. If you just look for chemistry of composition, a lot of times you're going to be, you'll have a lot of shortcomings. So unless you are just really wanting to do, if you do steel is one example where somehow, you know, if we talk about utility steel for any shop fabrication, sometimes you'll say, I want it at 1020, and we'll go with what that means later. So I'm just going to say AISI 1020, maybe one example where you can still see sometime on the drawing, that's all it's going to say. And that means a low carbon steel that has 0.2% carbon. In general, you also want to say, I want a certain mechanical performance. And when that's the case, let's say we just go one step up here. We can go to ASTM, is one example where if I specify a grade 36 steel, for example, that's telling me in KSI that my yield strength is going to be at minimum 36 KSI. We already moved up. And we'll continue that list as we go along today. Going with the process, going with quality control, inspection. This is probably, you know, kind of worst case scenario. If you just specify chemistry, you could, you know, not have steel. You could have wrought iron. It's an old way to make, before we had steel manufacturing, you could essentially take the iron and mechanically deform it until you collapse the inclusions and you become a little bit isolated here. And this is very, very, well, it's relatively ductile. It has very low strain hardening typically. Now this transition was in the late 1800s. So everything built, say, you know, starting 1920, around the beginning of the 1900s should be steel. But it just points to something that happened to me once where we suspected it wasn't steel, it was the wrought iron, just because there was a little bit more impurities than what we normally expect in modern steel. But it really wasn't a good way to tell, because the main difference here is the microstructure, whether you have the carbide and the inclusion all segregated, or whether you have the pearlite here. So this is not just carbon-based Fe3C. This also has ferrite in it. It looks dark, but this is about the same composition here. It's just the way it looks, and it just points out that if you're going to ask just for chemistry, you don't know what you're getting. So we talked about the AISI designation, the 1020 there. It's not completely uncommon. So in fabrication, sometimes you may have a 1045. In aerospace, you'll use, say, a 4340 here. These are all AISI kind of very common designation. If you have a 4340, we've talked about this at the very beginning of the class. I said, okay, well, you know, if you want to develop strength, you can go through quenching. But typically, you're also going to temper. So here, typically, it would be quench and temper. But just be very aware that this designation doesn't say anything about whether it's just going to be normalized, quench or tempered, and if it's quench and tempered, in which conditions. These are all parameters that essentially you have to determine and agree with the person that's going to do the fabrication. So there's a lot of reasons, I guess, if you don't want to make things complicated, to go one step up, and that was the example of the ASTM here. In ASTM, what you see is there's some tensile requirements. So it will give you the yield point minimum as 36, and it will give you a tensile strength range between 58 and 80. That's pretty precise to some extent, because now not only we have a minimum, and we also have a maximum on strength. So it's you know, one step up in terms of specifying the material. You can go, I mentioned the 36, but it's very typical with structural steel to go to a grade 50 instead of 36. That's in here we have one of them, very typical one of the designation. And one reason is you can still weld it very well at grade 50. If you keep going up in strength with steel, then it becomes harder to weld. So if you're building something that's going to require welding, it's the type of alloy that you want to use. They're going to have some ranges in chemistry that allow you to weld. They're also telling you a range of mechanical property that you want to get. So for this one here, there's just a minimum. There's no maximum. So this could be actually very strong, but the reason that there is a heat treatment on it, a chemistry requirement still allows you to weld it even if it was relatively high strength. Third example here that I selected, SAE, Society for Automotive Engineering. They also do a lot of the aerospace designations specification. If you call for a grade 8 bolt, now you're a little bit on a better tangent here, because they will give you chemistry, they will give you mechanical properties, and they'll say a little bit about how to do the heat treatment. So there are some ranges here, and it's based on you know, experience and trying to essentially always get the same product. If you use bolts for a certain application, they work well in cyclic load and fatigue. If you want to be able to have the same material over and over again. These are higher strength material on the grade 8, doesn't say here, but I think it's around 120 KSI that you start here for strength. So, for the yield. So we went up into our process here. So of course, the more you're gonna be pushing the capacity of the material, the more you're gonna be saying what you want precisely, so you don't have any issues during service. You can continue on. There's a lot of other types of designation. API will, the American Petroleum Institute will have its own set of designation. ASME would have a lot of requirement for material specification. So sometimes they'll use the AISI, but they'll say what they want for the heat treatment. The aerospace specification are a little bit different. Sometimes each company is going to say what they're looking for. So that's becomes a little bit beyond what I wanted to cover. But I think you get the idea here, right? I mean, the more you become specific, the more it's a demanding application, the more you should ask for. Now let's talk about other things you may want. Inspection or quality control. Of course, the AISI here for chemistry, if that's the only thing you're looking for, there's really not much quality control that goes with this. When you come to the SDM here and they have these minimum strength requirement, what is great about these standards, they also tell you how to do the testing. So if you say this is going to be a grade 50, it's going to have an elongation of 18%, they'll tell you the geometry of the specimen to use to do that test, and the strain rate, and how to analyze the data. So there's a lot. When you call one of these standards, it will call in perhaps 5 or 10 of some other standards on how to do the testing, how to do the quality control, how to do the chemistry analysis. So there is a lot of advantages. When you come to a more specific standard, the SAE, again, it will just have more into the processing of that bolt. Most of these standards, however, don't really tell you how to do it, how to design it, and what should be the conditions for it. These become more industry specific and speaks to the factor of safety, and we'll talk about that on Wednesday. But it gives you a good starting point here on how to think of how is the quality going to control. Very little here. Here there is some requirements. It doesn't say how to do the heat treatment. So here, in terms of processing the steel, in terms of what temperature you're going to deform it at, as long as you reach these tests, you're welcome to do any processing you want. When you come into more specific here, well, you have the temperature for forging. Sometimes they'll tell you where to take the samples, for example, for quality testing. That would be something specific that you want if you're looking at a very sophisticated equipment. Now, if we go to my original list, I said we had the material. We do have the process here. We have the quality. If it's a casting, you can ask for a number of non-destructive testing. You have, liquid penetrant is one. You can do mag particle. You can do ultrasonic if you want. There's a lot of levels here, and the list does go on. This one is typical if you're in aerospace, or even if it's something that was machined. A lot of times they'll still ask you to do testing to see that there's no flaws, surface flaws on the material. But these are not part of really the material requirements. When we starting here, I think is really where we're starting to depart, and we become on things that you need to specifically ask for in the specification. I wanted to talk a little bit about joining here because it does come into play if you're gonna have material. And this is where a lot of the issues come about. You know, if you have a plumbing system, that's an example we're going to see. What's more likely to fail is the actual copper pipe or the joint that was made, you know, in your basement or somewhere in the building. And the answer, a lot of times, it's how it's joined together. So I pulled out an example here of an ASTM standard that goes beyond just asking for material. The STM standards, you can have them for a variety of stuff. You have the testing method, then you have the material requirements, and here we're talking about joining requirements. So there's specifically, this is for soldering. So you essentially have to prepare the surface of the copper pipe. You put a flux, you insert it, you put heat, and then you have the filler alloy. This is the solder alloy here that's coming in. So you make a joint. We go here. Goes through the different steps of what needs to happen. One thing that is very interesting in this whole list, it doesn't say how you're going to control the quality. That was our topic here. And it doesn't tell you either what is acceptable or not acceptable. Essentially, and I wish I brought one of those today, but I have a bunch of those that do have incomplete filling because you're relying on the good preparation to have the capillarity force to bring that solder in the little interspace between the two parts. This is a sucker joint. You put one in the other when you heat it up with the flux. Just by surface tension, the molten solder prefers to be between two pieces of metal as opposed to just be standing in air, so it will suck into the capillarity as long as it's clean, and that there is flux to keep it clean as you heat it up. So just to speak, because we're in this topic, with what you can ask in your specification for a plumbing system, you say, okay, well, I'm going to be at 80 psi pressure in the house. Why don't you test my plumbing system at 125 psi? See, but you have to say that. If you don't say it, then you're becoming a little bit more, well, I guess that's what people do, so you should do it, and those sorts of things. Yes?
How do you strike the balance between doing something that has enough of a safety factor that you're confident your system's not going to be damaged, but not damaging that your system is sound, but not damaging the system in that process? Because imagine if you cranked up the PSI high enough, you could damage the system.
Yes. So that's a very good question. So it speaks to kind of any proof test. You know, in a proof test for a pressure vessel, it's exactly what you want to do. You say, I'm going to load it enough that I know I don't have a big problem. At the same time, I don't want to change the geometry all of a sudden and generate cracks. That's where you're going, I think. So for plumbing, it's very simple in the sense that 130 psi, it's still very, very low. These lines should be able to take, 500. One of the reasons for not going too high is just safety. If you have some air in the system, by the way, you have to do that with water a lot of times. If you do it with air and you do have a separation, it's a little bit like a garden hose. It's going to start dancing on you. So it's good to have fluid when you do a proof test. It's a liquid. So in terms of just the generality of introducing the effect, most of the times it won't happen. If it's ductile, all it's going to do is deform a little bit. Now there may be some cases where you would like to do the the liquid penetrant and the mag particle after you've done a proof test on a pressure vessel, for example. So if there was something brittle and you generate a little crack, now you get the chance to pick it up. And that would be a very good example, because sometimes it will not completely break, but that little crack that you generated at that point can continue on to the surface. Thank you. So, we could definitely go on to how we specify here. But that's, I was going to talk about joining. So we have this ASTM, and it's very, very simple. It's just a procedure. If you follow these steps, you meet our standard. Is the joint good? We don't know. So that was our problem there. If we go into fusion welding, there's the American Welding Society. And that is a lot more comprehensive. American Welding Society will have some basic inspection requirements. They'll say, go to the weld and see how the bead looks like. Is there a lack of fusion? We have certain characteristic that, I wish we could go into more details here, but so it's going to be on the geometry. It will also have procedures, and before that, it will even go into some extent into the design. So it will give you some values, some nominal ways to calculate strength of joints. So by far here on what we have on the board, that's the more comprehensive standard. It's really going all the way from design, procedure, the geometry, I guess, is part of the procedure. Then you have you're going to have the fabrication, so they even tell you a little bit, some basic stuff on fabrication, and then the quality control. Now, we can't fool ourselves into this, that the quality control is very comprehensive. At the very basic, the AWS is a visual inspection that can be done by the contractor himself. So it's not a whole lot more than just saying, go do your things. But there are some parts in here, there are certified welding inspectors, for example, from AWS, that can come and independently verify that you meet those requirements here. Or you can go a few steps up and say, I'm going to have some additional non-destructive testing done on my welds, and that all of a sudden here applies additional description and acceptance criteria. So AWS will include non-destructive testing, but most of it's optional. You have to ask for it if you want them to do it according to AWS. So what I used to do working with structural engineers and mechanical engineers is we'll say, do all of this, do your welding procedure, your fabrication, and your quality control for AWS. And now all of a sudden you're calling a piece of a code that is, about this thick, that will have a lot of extra and very detailed requirements. But these are all for very standard fabrication. Now, of course, you have different welding codes, depending if you're doing a pressure vessel, if you're doing a structure, if you're doing a bridge, for example, is specific AWS codes for that. There's some for stainless steel. So it gets very detailed as you move along, and if joining is important, then of course you should say something about it, how you're going to want it done. We'll go through a pretty interesting example, I think, that's going to tie in some of what we've talked about and some of what we're going to talk about on Wednesday and Monday. It's a crane that collapsed back in 2007. This was one of my first projects, graduating with my PhD. Just went on. It was one of the first things, just had to take field notes and and start working. You don't see very well here. What they were doing is building the bypass bridge for their Hoover Dam. It's off Las Vegas. So this is tying Nevada and Arizona to essentially increase and make the traffic more sustainable. So the arch here is what they were building, and these came in segments that were of concrete pre-made. So they had a shop there just off-site to cast the concrete segment and post-tension it, so you can get all the compression in each segment. Then they will bring it with that cable crane, so I think you can see it here. So you see the two illuminated towels. There's one here, there's one there, and that's a half-mile span. And what you see is the little trolley that's over here that is carrying it from one side to where it needs to be put on. It's a relatively sophisticated system where if we look at the two towers here, they can lean this way, so you can cover the entire span or width of the bridge here. So if you gotta go 100 feet, it will lean 10 degrees one side, 10 degrees the other side. And then, of course, the trolley is shared between the two cables, so it's more stable. It doesn't tend to fluctuate as much. Now, this one with all the lights was the replacement crane. So the reason I got involved is the first one failed. Thankfully, there wasn't anybody working on the site at that point. It was a really fortunate situation that it failed during a storm, because they would actually carry some workers. They're not supposed to do it because it doesn't have the OSHA factor of safety for carrying people, but they were carrying people on that trolley instead of having them ramp up the arch to get the day started. So it's always, you know, which one is safer, I guess. I've seen them do both. So okay, it failed. This is a little bit of really how it works. Is you have about, I don't know, we didn't really make an inventory, but maybe we had 500 or 600 broken connections between the 4 different towers. And the big question was, why did it fail? So that, of course, you can go into the first of all, you have to see if there was something done special. Maybe it was supposed to be tied down and it wasn't tied down, so this must be the reason. And then once you're done going through the very simple stuff, well, somebody just let it go. You can start looking at what the metal tells you. So that's really what we did here. And there was one tower that was, I would say, interesting. Because this is the bottom of the tower here, so it's funneling from very small to bigger, so it's on a pivot point. And what happens is what you have on top of the base is the metal of the tower. So in this one, it's just instead of just leaning over, it crumbled in place. You have the bottom that went on one side, and that way is the top of it. So something buckled on the interior structure of it. And the first thing to do was to see where this could start on that specific tower. So over here, I just show a little bit of a diagram where just by going through the debris, we just created an inventory of how each connection failed. Is it just a pull? Is it just bent? Because if it's bent or crushed, that's a consequential effect. The most likely thing to start here is just a straight pull. So we were essentially looking for straight tubes that were just pulled out without anything else, because that's where it's more likely to break, especially because you'll see there were a bunch of welded connections. So this is always interesting to see, how other structures behave. So we're looking here at another area, and this is a an interesting design for tubes. So tubes are great because for just a small weight of material, you can be fairly resistant to buckling. If you take a bar or an angle, you don't get the compression capacity that you get with a rounded tube, like you have. Do I show the rounded tube? Well, over here, what you have is, this is the tube, and this is just a flat plate. In that case, it was the corner, the four corners of the tower. So if I get the tube to insert into the plate, I essentially make a gusset connection, and I can weld on each side. So this is the weld on top, and then you would have another weld on the other side. And those welds are essentially acting in shear. So if you can do that, it's great, because now all of a sudden the component that's more likely to fail is not loaded in tension locally anymore, it's loaded in shear. I made that last year because I could tell I said gusset connection, nobody knew what it was. So this is what it is. It's very useful. It's used a lot, in kind of space shuttles and things like that, because you can make them with bolts, you can make them any way you want, but you're essentially transferring instead of, it's the opposite of what you see in most airports. Most airports just have a big tube and it's welded all around, so it's not optimized for cyclic load or strain. So this tower did have cyclic load, and one of the issues, I'm not going to say it's the only one, but one of the issues is they welded this little corner here. So over here we're looking straight down, and what happened is the tube cracked from one little end of the slot to the next one, all around here, and it failed by fatigue. And the reason really for this mode of failure is they welded these end of the tube. So perhaps the only reason I can think of why you do that is to try to prevent moisture from penetrating, but you still have access through the end anyway. So there will be some, and you have access to the top too. So there's still going to be, rain or any moisture penetrating into that tube. So the real way, and it's described in the AASHTO code for bridges to make this, is you don't weld that corner, because all of a sudden if you do that, you have the bead here loaded in tension, as opposed to just in shear like you'll have on the side. So it's a very simple thought. Like the idea of having those gussets is to avoid tension in the tube, and now all of a sudden they included them. So that was the reason for these fatigue cracks. And it turns out on this structure, they had a number of other issues. First of all, they probably should have known about cracks, because some of those tubes had repair patches. So somebody went in and said, oh, I got a crack here, I'm gonna reinforce it. So it's not a great thing. What the replacement was essentially a very, very similar design, except that instead of connecting directly here to the attachment plate, they had smaller. No, this is just the leg. So you got 4 legs on that tower. So instead of connecting directly to the leg, they had actual gusset plates included. And they just sized everything up, and they didn't put any welding here. It was just very clearly specified. And then you have, perhaps for a cyclic load, for the idea that you're going to go back and forth, maybe you have 5 times more strength all of a sudden, in terms of resistance against cracking for the same amount of speed. So it speaks to the design, and even AWS here, what I would consider a kind of a good baseline welding code, will tell you the difference in terms of if you do have cyclic load. It will tell you the difference between a weld loaded in shear versus a weld loaded in tension. I just spoke recently to somebody that also investigated this from a different perspective, and they did have some information that apparently there's a cable that broke in this whole sequence in terms of the triggering event. And, you know, I can't, it will make sense because one thing that I do remember saying is, say you have the tower here. So it goes from a triangle to a square, that goes up. And you have the triangle again on top. So over here. So this is where you're going across, and then you have a back stake to hold everything together. And there's, well, I'll show you an image of this one on Wednesday because it's very relevant to what we're looking at. There is a big Z section here. No, just a regular W. Lined up this way, and there's a big track that started right here that I could not explain. So there's some indication that there were two of these, and one of them broke, which would overload in a dynamic way the other, and causing it to start a crack. Now, it still doesn't explain why the other tower crumbled as opposed to just leaning and falling on one side. So there's no doubt that the tower that I showed you images on was very weak. But when it's, again, there's so many components involved, there's always a possibility that something else was going on. So that was, you know, one of those things here. And I do remember, that was 7 years ago, looking at this factor, thinking, so where did the load come from to generate this? And of course, doubling the load almost instantaneously is one way to make that steel fail in a more brittle way that you'll expect it to fail. I mean, this was very warm weather. Of course, it was a very thick section, so here we're looking about probably 18 inches deep, so something that literally is about this in size. So this thickness was more than an inch in size. So there's no way that that the manufacturing of this is perfect when you make a steel beam of this size. So of course there were a few little inclusions down there at the initiation site, but all of that doesn't explain why it didn't stretch before it broke. So the idea that it was loaded dynamically would support this being also one of these here. Now, it could be loaded dynamically as the other crane collapses and then all of a sudden pull on it. So, so this examination here doesn't tell you if this is a consequential effect or if it's the initiator. That's a difficulty. So that's a little bit what I, you know, a lot of times I think you heard or you have the ideas, we do get calls from attorneys or insurance companies to look into a failure analysis, and of course they do have a purpose. You know, they want to know if it's their problem or if somebody else did a mistake. But in some cases, like this crane collapse, I think there's also a good set of lessons to learn when you go through this investigation in terms of, you know, maybe that's not the only factor, but really, you know, you could have done a better welded joint. Or here you could have another design that when you put loading on a very, very large beam and tension. So these are all things that, and the last lecture, so that will be next Monday, I'll talk, for example, a little bit about the World Trade Center and some of the analysis that was not done by NIST on it. And you'll see that there's been changes. There's been changes to the building code because people did realize, oh, we can do this stuff. So it's the hard way to learn, but it does happen. Thank you.